In today's video, we will learn about rotational motion under constant angular acceleration. We see that the equations for rotational motion under constant angular acceleration are similar to linear motion under constant acceleration equations, with only the names of the variables that differ. So down below, we see the differences between our linear motion and our angular. We see for linear, our displacement was symbolized by x, and with angular is symbolized by theta. Our velocity is symbolized by v, and our angular velocity is symbolized by omega. Our linear acceleration was written as a, and our angular acceleration is written as alpha. So if we compare the equations for rotational and linear motion, we see that the equations are the same, only our linear expression is substituted with our rotational motion constants of theta, omega, and alpha, which are summarized below. In our first example, it states that the blades of an electric blender are whirling with an angular velocity of 375 radians per second. When the blend button is pressed, the blades accelerate and reach a greater angular velocity after the blades have rotated through an angular displacement of 44 radians. The angular acceleration has a constant value of 1,740 radians per second squared, and we're asked to find the angular velocity of the blades. First, if we summarize the information that we are given, we see that our initial angular velocity is a positive 375 radians per second, and that our angular displacement of the blades is equal to 44 radians, and the blades of the blender have an angular acceleration that is equal to a positive value of 1,740 radians per second squared. And we're asked to find what is the final angular velocity of the blades. We see that we have an equation that states that our final angular velocity squared is equal to our initial angular velocity squared plus 2 times our angular acceleration times our change in our angular displacement. Since our initial angular velocity is given to us, as well as our angular acceleration and angular displacement, we can solve for our final angular velocity. So if we simplify our equation to get our final angular velocity by itself, we see that our final angular velocity is equivalent to taking the square root of our initial angular velocity squared plus 2 times our angular acceleration times our change in our angular displacement. And if we plug in our values, we see that our initial angular velocity was 375 radians squared plus 2 times our angular acceleration of 1,740 radians per second squared times our change in our angular displacement of 44 radians. If we take the square root of these values, we see that our final angular velocity is equal to 542 radians per second. In our second example, it states that a dentist's drill starts from rest, and after 3.2 seconds of constant angular acceleration, it turns at a rate of 2.51 times 10 to the fourth power revolutions per minute. We're asked to find the drill's angular acceleration. First, if we summarize the information we're given, we see that our initial angular velocity is equal to 0 radians per second. Our final angular velocity is equal to 2.51 times 10 to the fourth revolutions per minute. And our change in time is 3.2 seconds. And we're asked to find the angular acceleration of the drill and its angular displacement. So in part A, we are given the equation where our final angular velocity is equal to our initial angular velocity plus our angular acceleration times time. We know our final angular velocity as well as our initial angular velocity and the amount of time we can solve for our angular acceleration. If we rewrite the equation to get our angular acceleration by itself, we see we'll have our final angular velocity minus our initial angular velocity divided by time. However, we see that our initial angular velocity is in radians per second, and our final angular velocity is given to us in revolutions per minute. First, we must convert our final angular velocity of revolutions per minute into radians per second. So we see that our final angular velocity is 2.51 times 10 to the fourth revolutions per minute. And we know that for one revolution is equal to 2 pi. So when we multiply this out, we see that our revolutions will cancel. And now we're left with radians over minutes. And in order to get minutes into seconds, we know that for 1 minute, there are 60 seconds. We'll be left with our final angular velocity in radians per second, which comes out to be 2,628 radians per second. So now that our final angular velocity is in radians per second, we can plug it into our equation so we can solve for our angular acceleration. So our final angular velocity is 2,628 radians per second minus our initial angular velocity of 0 radians per second divided by our change in time, which happens to be 3.2 seconds. And when we subtract and divide this out, we see that our angular acceleration is equal to 821 radians per second squared. In part B, we're asked to determine the angular displacement through which the drill rotates during this period. So in part B, an equation we have that we can solve for our angular displacement is our angular displacement is equal to our initial angular velocity times time plus 1/2 our angular acceleration times our time squared. And since we aren't missing any variables, we can solve for our angular displacement. Since our initial angular displacement is 0, and 0 times our amount of time will be equal to 0, plus 1/2 our angular acceleration of 821 radians per second squared times our time of 3.2 seconds squared. And when we calculate this out, we see that our angular displacement will be equal to 4,203.5 radians.